in the last class, first of all, we talked of this equation for pressure, del square P is equal to minus rho. Yeah.
So the course you were saying 711, where is it added in Google? 7.
अच्छा बाद में देख लेंगे at the end of the class. Okay. So this is what we said was the equation for pressure. If you want a direct equation for pressure, and this we said is the Poisson equation for pressure. Now, in addition, we will be using the vorticity equation, and again I am going to just give you the vorticity equation without deriving it. I will just maybe tell you how it is derived, but I will not be deriving it. Vorticity, we write it as del cross U. So, if we take del cross equation C from last lecture. Okay. So, what we get is this is what is termed as the vorticity equation. Now, we have not done the derivation. I have not covered the tensor notation, otherwise we could have easily derived this from by doing this operation. If we take a del cross of the Navier-Stokes equation, we get the equation for vorticity. Okay. Now, notice the pressure term is missing. Now, why does that happen? Because there are two identities. One is, sorry, DC, sorry. Divergence of curl of any quantity is 0 and curl of gradient of any quantity is 0, and this is for any quantity which is there. This follows the mathematical nature of the equations, that divergence of a curl is always 0. Whatever you take, whatever is this function, and similarly curl of a gradient is 0. And what is curl? Do you all remember? Curl is del cross, okay, or cross product, curl of a gradient, and divergence is del dot. Okay. So, now by this definition, the first, what is omega? Omega is curl of velocity, del cross B. So, therefore, divergence of omega is always 0. By definition, so this leads to del dot omega is always 0. Whatever, it does not require the flow to be incompressible or anything. By definition of vorticity, del dot omega is always 0. And similarly, when I say curl of the gradient, now the pressure term in the Navier-Stokes equation occurs as a gradient. So, when you take the curl of the equation of the Navier-Stokes equation, then the pressure term automatically vanishes. It just does not stay in the vorticity equation. Okay? So, this is the vorticity equation. Now, if you look at the vorticity equation, the vorticity equation is very similar. So, now versus Navier-Stokes equations, one is no pressure term in vorticity equation. Two, there is an extra term omega dot grad u in the vorticity equation. Otherwise, the two equations look exactly the same. The pressure term goes away and there is this extra term omega dot grad u. Okay? Otherwise, on the right hand side you have a nu del square omega, there it is nu del square v, left hand side is again the same. Okay, so that you call these as transport equations. It's a transport equation for vorticity. And what we have there is this extra term, and this extra term omega dot grad u, this is called the vortex stretching term. And we will look at more of the physics of this when we talk of vorticity equation and vorticity fluctuations. But you will have to start from the vorticity equation which I have written there, and maybe I can write this equation as D. If I want to refer to the vorticity equation, I will now call it as D. Okay. Now, obviously, one thing, if you try to look, if the flow is two dimensional, then for 2D flow, velocity will be equal to Vxi plus Vyj, and Vx and Vy will be functions of xy. Okay. And omega, which is equal to del cross V, this will be omega k, because velocity, if you look at it, omega will be equal to I j k d by dx, d by dy, d by dz, and this is Vx, Vy, Vz, and this Vz will be 0 and d by dz will be 0. So, omega is omega k, because I component of vorticity, you take I is d by dy, this is 0 and this is 0, will be 0. J component again, this multiplied by this is 0, k component will be non-zero. Now, when you do omega dot grad, omega dot grad will become omega k, or omega, the component of omega in the k direction, times partial by partial z. Okay, because it will be omega I component partial by partial x plus omega j component partial by partial y plus omega k component partial by partial z. Omega has only got k component, so it's omega partial by partial z. And when this operates on velocity, velocity is not a function of z. So omega dot grad u is 0 for two-dimensional flows. This we should keep in mind because we will use this later. So that's why I'm doing this now. So for two-dimensional flows, omega dot grad of u is equal to 0. Whatever be the form of u, whatever be the form of omega, this term is identically 0. Because see, this will have connotations when we talk of turbulence. Because what we will see is that basically the vortex stretching term plays an important role for the turbulent for eddies to break up and all. So therefore, when this term is 0, then it will relatively not be possible for eddies to be stretched and to be broken. And that sort of links with the thing which we said, that turbulence is a three-dimensional phenomena. In two-dimensional, because of the vortex being unable to stretch, the flows, two-dimensional flows are generally not turbulent. There are very special classes of flow which you call 2D turbulence, but otherwise all turbulent flows are three-dimensional. Because vorticity has to play an important role, and for this vorticity to be created and to be broken at small scales, we need the vortex stretching term. And this term is 0 in two-dimensional flows. Okay? Yeah.
So like, as we say that 2D flows are not turbulent.
Yeah.
Flows are not turbulent. So like, I mean like when we see some simulation done at very high Reynolds numbers, so those flows will not be turbulent. So how do we
Now, what simulations do you see? Simulations of which quantity? Is it, are you talking of Reynolds average flows, mean flows, or are you talking of LES and DNS? RANs. So I'll come to that. See, in RANs, what we are doing is all the three-dimensional effects are being captured in the mean velocity. So the mean velocity flows, the mean flows will be two-dimensional, but the instantaneous flow will not be two-dimensional. When you take a mean of it, then the mean is two-dimensional, and that is why when you talk of RANs and you talk of K epsilon type of models, you do see only two components of velocity or only one, and that happens. So let's go through this whole. In fact, some of these concepts are what I want you to be at least clear of by the time we leave the course. So, but the instantaneous velocity is always three-dimensional. The mean will not be three-dimensional. And that is, in fact, this is, even I had this doubt when I studied turbulence. Three-dimensional कह रहे हैं, three-dimensional है, solve तो हम केवल mean of u कर रहे हैं, we are not even solving mean of v, mean of w. So the mean terms will not be three-dimensional, but these the fluctuations will be. Then there is another equation. So this is the last equation I am going to look at, which is the equation for a passive scalar. And this again we have seen this, like for example this could be temperature, concentration, and for temperature this is a case where gravity or where buoyancy is not being considered, because if buoyancy effects are being considered, then the Navier-Stokes equations themselves will change. A gravity term comes in the Navier-Stokes equation, but this is when temperature is like a passive scalar. So in those cases what happens is that we decouple the temperature equation and the velocity equation. So we first solve the velocity equation, and using the velocity field we solve for temperature or concentration. And here the equation takes a very simple form: partial phi by partial t plus u dot grad of phi is equal to some coefficient gamma times del square phi. We have seen this equation when we talked of the temperature in the room, and we talked of the, but there of course we saw more complex form. We also added the gravitational buoyancy term to this, g times delta theta upon theta. So this is an equation for a passive scalar, and we will be manipulating all these equations or looking at these when we talk of turbulence. So these are equations for instantaneous quantities. All these equations which I have shown, the equation for vorticity, the equation for phi, or the equation for velocity, and the continuity equation. Now vorticity is not an independent equation. It is derived from the Navier-Stokes. So either we solve for velocity or we solve for omega. Now of course somebody may say, well, why don't we solve for omega and then invert to get velocity? It is not so easy to do that, but can be done. And again involves green functions, things like that, to get velocity from omega. Now before we move to the averaging, let us look at some tools and definitions for statistical turbulence. Okay. Now as we saw in the first class, when I talked, I said that when we take mean quantities or averaged quantities, then what we find is the averaged quantities do not vary. For example, in a lot of flows, if you take time average, then that does not change at all. So we talk of taking averages. And why do we take averages? Because we have firstly all the fields. So instantaneous fields, instantaneous quantities, and here we say like velocity, temperature, concentration, in etc. In turbulent flows, they behave like random variables or random functions. So we assume, for example, the velocity field u, which is a function of x and t, is a random function. So that means you fix up a particular x, and if you see the signal as a function of time, you will find this to fluctuate. Okay. So this behaves, that is what we say, that behaves like a random function, and so this is u at a given x0 as a function of time. So now if we want to take the average of this, we are assuming right now that it is a function of x and t. So at each x it is changing, at each t it is changing. So for example, this is at a particular point in a wind tunnel, there is flow taking place and you are measuring the u here. So this point is what I am saying is x0. So then what you do is you perform n experiments, where n is some reasonably large number, and then you keep on measuring u. Let's say you start the experiment at time t is equal to 10. At this x0, you measure u. Do the experiment again with the same conditions. At time t is equal to 10, measure u at the same point again. You keep on doing this experiment n times. So then the average which you take is what you term as the average of u. That means you have done 10 times or 100 times. So u1, let's say first is u1, second is u2, third is u3. So u1 plus u2 plus u3 up to plus u100 divided by 100. You do it 95 times, then you do 95 divided by 95. And you keep on doing it a large number of times and take the average of these. That is actually what we mean by average. Okay? So you perform each experiment is called a realization, and n realizations take average, and that is what we say is the mean. So this term, what we say, this average is called ensemble average. This is the average, is the statistical average performed on large number of realization. Large number of, actually we should add another term here, independent realization. It means we do the experiment once, do it again, each of them are independent, and when we carry out the average, we call that as an ensemble average. And we will denote it by angular bracket, or certain books use an over bar. We will use both of these simultaneously. This is angular bracket So, for example, average of U alpha is denoted by limit n tends to infinity 1 over n sigma of U alpha ith realization I going from 1 to n. So, this is the meaning of the average. Is this clear? Now, I have just alpha means I am talking of one velocity component, it could be a second one, third one, it could be a scalar. So, in a turbulent flow, of course, temperature will also fluctuate. So, to carry out the average, technically what you have to do is, you have to do, now how large is n? Well, once the average stops varying, you do one experiment, you add a second one, take the average, you do the third one, you will find the average for 2 and 3 will not matter, will change. But you keep on doing, after some n, you will find when you do for 100 and for 101, let us say it stops changing for that n. So, then you can say we have reached enough number of quantities. Okay? So, that is how, this is technically the meaning of average. Okay? Now, what we have seen, often you see in courses and all, we say we take time average or space average. So why do we do that? Let's see that. But before we do that, let's also talk of quantity number 2, which is, no, this is not space. This is each experiment being done, because that's why x also is a variable. So you do experiment number 1, you start the experiment. After the experiment is started, let us say at time 20, you take at a particular location the value of the velocity. Band kar do experiment. Start the experiment again. At time t is equal to 20, at that place you measure the velocity again. Stop it. Keep on doing this. Now, of course, you realize it's a very tedious thing. It's not possible to do this for practically for any of these things, except numerically also it's not possible, because to do each of the numerical runs takes you enough time. It's not easy to solve these things directly on the computer. Okay? So this is the meaning of the average which we say, and it is the ensemble average. Now before I talk of what else to replace it with, let's also look at more averages, which is, let's look at moment, and we talk of nth order moment of the velocity field is the ensemble average of any tensor product of n components of the velocity field. And let me explain it by example. Let's say a moment of order 1 will mean I have to take only one component of the velocity field. So let us say I take mean of u alpha. So I have taken one component u1, u2, u3, and I take its mean. So this is the moment of order 1. In moment of order 2, what I am going to do? I will be multiplying two components of velocity. I will take a tensor product will be, so that means moment of order 2 this will be mean of u alpha times u beta. So two components of velocity. Now alpha could be equal to beta also. Then it will be mean of u1, u1. If alpha is 1, beta is 2, it will be mean of u1, u2, and so on. If alpha is 1, beta is 3, alpha beta cannot go more than 3, because these are velocity components. So that means totally this will have 9 components. Mean of u1, u1, mean of u1, u2, mean of u1, u3, mean of u2, u1, u2, u2, and so on. So there will be total 9 components, and of which the symmetric components will be equal. Mean of u1, u2 or u2, u1, because the product is the same, so their mean will also be the same. Okay. So this is what we call as mean of order 2, and in fact we'll have to justify it more, because now I've just written it as u alpha, u beta, but are they at the same location or they are at different locations? I have not specified that right now. They could be at different locations also, then you have to talk of mean of a different type, but in general this is the moment of order 2. Okay. And then of course whether they are of mean quantities, fluctuating quantities, I have not talked of, but and normally this is called the correlation tensor. I am trying to introduce some of these terms and actual definition of these will follow, but and then similarly if I want to get moment of order 3, this will be mean of u alpha u beta u, sorry let me just change this, gamma कर देते हैं इसको ना अल्फा बीटा के बाद yuga. So this is a third order correlation or whatever, and we can go to more and more orders. And again, right now I have taken this of instantaneous quantity, but normally what you will realize is these are taking of the fluctuations. I have not even defined what fluctuations are. We did some of the qualitative definition in the first class. That you subtract the mean, the remaining is called a fluctuation. But normally these correlations which we take in turbulence are of the fluctuating quantities. But so next now, yep. Okay. So then we talk of something called homogeneous turbulent flows, or a property called as homogeneity. And a turbulent flow is homogeneous if all the statistical properties concerning a set of n points x1, x2 up to xn at time t1, t2 up to tn are invariants under the translation of x1, x2 up to xn. And what we mean by this is, for example, if I have u alpha 1 at x1 comma t1 multiplied by u alpha 2 at x2 comma t2. Let me just take a simple, it could be any average. I am just looking at a second order average. This I am just talking of this, I have not completed this, but just for illustration I am showing a second order average. This will be equal to u alpha 1 at x1 plus r comma t1 times u alpha 2 at x2 plus r comma t2. That means, let us try to see. This is point x1 and I am looking at velocity component at x1, and if I have another point x2 and I am looking at, let us say this is u alpha 1, this is u alpha 2. I am looking at the velocity component at x1 multiplied by the u2 component, alpha 2 is 2, alpha 1 is 1. I am looking at this product, whatever is u alpha 1 multiplied by u alpha 2, and at x1 and x2, where now if I go to any other x1, see these x1 and x2 are separated by a vector r. Now homogeneous means if I calculate this average at this point and over n experiments, but now I go to another x1 and I go to another x1 plus r. So x1 plus r will be somewhere here, exactly the same distance from here. And if I look at u alpha 1 and u alpha 2, then this average is only dependent on the separation. It does not depend on which x1 I am taking. The average over the entire region is only a function of the separation. It is not a function of the particular x1 at which or x2 at which I am taking the location, the separation. Actually, these should be vectors. I have made it as a simple one dimensional thing here, but these would be actually vectors. Okay. So this is what is meant by homogeneous, that, and it's not one average. Any average which you take, that average will not depend on the individual location. It will just depend on the separation. So this is what is meant by a homogeneous flow. So that means that is in a homogeneous flow, statistics do not depend on the origin they only depend on the separation. And this statistics is first order, second order, third order, everything. Now, as an example, so in a homogeneous flow, mean of u alpha at x comma t will be equal to the mean of u alpha at x plus r comma t, because it depends only on the separation. So if I take just a first order moment, then first order moment, this mean should at any x should be the same at any other location. So that means this mean in a homogeneous flow should not depend on x, because whether you take the mean at this value or this value or this value, all moments are the same. See, there earlier it was a second order moment, so we had a separation. Now this is only one quantity. So this quantity should be the same at any location. There is no separation now. So in a homogeneous flow, what we have is the mean of u alpha by dx must be 0. So mean velocity in a homogeneous flow is not a function of the spatial coordinates. This is if we are talking of a homogeneous flow in all the three directions. Now we could have a turbulent flow which is homogeneous in one or two directions and not the other directions. So this will imply mean velocity will not vary along the directions in which flow is homogeneous. Now, probably taking some time to grasp this, but let me first give an example of this. Because an example of a flow which is homogeneous in all the three directions, that means basically the mean velocity is either constant or is zero, is an example when we have in a wind tunnel, if you have just a flow which is what we call as the decaying turbulence, that you have just small scale turbulence and you just leave it. So then there is no mean velocity, there is only fluctuations. Then we have a flow called a turbulent boundary layer or turbulent channel flow. What we mean by this is a turbulent boundary layer will be just, let this be the x direction, or x1, this vertical direction is x2 and this direction is x3. Okay. So x2 is the direction which is perpendicular to the wall. x3 is this direction which is a tangent to the wall coming out of the board. x1 is the flow direction. Are the three directions clear? Now here, so we have, I can maybe plot it better like this, that this is here, so this is the x1 direction, this is x2, this is x3. Now unfortunately the people in atmospheric sciences have gone. In atmospheric sciences, they use a different notation. The z direction is taken as the vertical direction. So if you see any of the atmospheric science type of papers, this will be termed as x3, not x2. So I think somebody said that the meteorologist has his z axis in the clouds. So whereas for us it is the y axis. So this is the boundary layer, and in a channel flow this is basically the same flow, but there is a flow at the top also. Now here what you will expect is the mean velocity, if you take the means and sample average or whatever, so it has to depend on x2, because x2, the velocity, any velocity at the wall has to be 0, no slip boundary condition. As you go up, the mean velocity increases. So therefore, in a flow like this, in this boundary layer type of flow, the mean velocity profile takes a shape like this. And this shape will be different for laminar or turbulent flows, but in a turbulent flow, typically this is like this. And then we ask, is the flow homogeneous in x1, x2 and x3 directions? Now, what do we expect? In x2 direction, clearly, as we know, the velocity here is 0, it is equal to capital U somewhere at the top, so it is changing with x2. So, flow is definitely not homogeneous in x2 direction. Is that clear? Now, if this plate is wide enough perpendicular to the board, and if we neglect the end effects, then in the x3 direction, we would expect the flow to be homogeneous. That whatever averages we take, if I in the x3 direction, if I move, then it should just depend on the gap between the 2 points. It should not depend on the origin, because nothing is changing across x3 as such. So even in a turbulent flow, instantaneous things will change, but averages will not change across x3. Yep.
In a flow, according to the previous statement, in a flow, if I have a pipe which is sending out water, and so I'm just thinking about a flow in which it diverges like this. So is that not a homogeneous flow?
No, so diverging flow, we are not really talking of here, this example, because this example we have flow in a channel or something like that. So this is not a diverging flow. In a diverging flow, things will be different. Now diverging flow, again, if the x3 dimension is infinite, if you are talking of a divergence like this, but which goes up to very large dimensions along x3, then again you would expect x3 to be homogeneous. Okay. So x3 direction is homogeneous, and in these flows, this is an example of a shear flow where the velocity, bulk of the velocity is in the x1 direction. If you look at the mean velocity, its component will be mainly x1. Bulk of the velocity is in the x1 direction. So then, now in the x1 direction, what happens is, at the start the flow will not be homogeneous, but once it becomes sort of what we call fully developed, then in the x1 direction also the averages will not change. So once we are away from the origin, homogeneous but away from the start. So sufficiently downstream, we expect the flow to be homogeneous in the x1 direction also.
So how are the cases you are saying different from laminar flow?
The difference is that what we are talking of are only the means. If I look at the velocity in a laminar flow, the velocity will be just u1, which is a function of x2. Here if I look at u1, u2, u3, all of them will not be 0. And they will be functions of time also. But the means will follow this. So this homogeneity and all is for averages. not for instantaneous. What we have deduced for instantaneous quantities or for means, if they are also valid for instantaneous quantities, then the flow will be laminar. But here it is only the statistics which behaves like this. So, and then we also define a ui at x comma t times uj at x plus r comma t plus tau. This is a general definition. This is termed as the second order correlation Rij, which is a function of R, T and tau if the flow for a homogeneous flow, basically the correlation will only depend on R, it will not depend on X, and that is the basic meaning of homogeneous flow. Now, in statistics we have the ergodic hypothesis, which allows us to calculate an ensemble average as a space average if the flow is homogeneous. So that means what we are saying is that instead of doing, if we have some homogeneous directions, then instead of calculating an ensemble average, if we calculate a space average over the homogeneous direction, then that is the same as the ensemble average. And this is because across that direction, across the homogeneous directions, the means are not changing. So it is as if you take mean between two different points. It is as if you are taking a different realization. The same value at another point is like it is another realization. So, and this is what we mean by, this comes from what is called the ergodic hypothesis. And so, and the same thing, the next thing we will talk about is a stationary flow, which means what we are talking of space if the same thing is valid in time. And if the flow is stationary, then you can take a time average instead of ensemble average. And that is what we have done when we talk of taking a time average. And so that is the next thing which comes in, and maybe I'll do that in the next class, the stationary flows. And I'll just talk about stationary and isotropic flows, and then we will go back to the Navier-Stokes equation and calculate the average, so that we have made these concepts very clear. Okay? So in the next class we will be talking about the a couple of stationary flows and isotropic flows, and then averaging of the Navier-Stokes equation. That is what we will do. We will look at some of the rules of averages and follow from them. Okay. Now, again, आज काफ़ी सारे लोग, कोई अंडर ग्रेजुएट है या मतलब उन्हें यू आर फ्रॉम द मैकेनिकल और अप्लाइड हैं, अप्लाइड के हो ना दोनों, तो कितने लोगों ने अंडर ग्रेजुएट्स ने ये बंद कर सकते हो?